Hi everyone, welcome back to the channel. If you're new here, my name is Ryan, and today I'm going to go through this FE exam fluid mechanics problem with you. You can click on the first link in the description below to solve this problem for free alongside me interactively. It'll take you to a screen just like this, where you have the ability to flag questions. That'll reveal to you all the problems that we've done in our FE exam playlist. They all link back to video solutions. You can input an answer, see that video solution just like this, and you can see there's references to the actual FE exam manual with page numbers, section headings, and yeah, once you get the right answer, you can go ahead and input it here, and you can move on to the next question. So these will be great refresher for you if you're going to take your FE exam soon, especially this question. So go ahead and try it out, and let me know in the comments below if you got the correct answer. Let's get into the solution. The figure shows water flowing steadily through a horizontal circular pipe at section A. The velocity profile is linear, increasing from 0 at the pipe wall to a maximum of 5 feet per second at the pipe center line. The pipe has a diameter of 6 inches. Assuming the density of water is 1.94 slugs per cubic foot, what is the mass flow rate at section A? Okay, so first thing I'm noticing is that this problem is in English units, and the truth is on your FE exam, you're going to have some problems in English units, so it's a good idea to get familiarized with it now. Let's write down some of our knowns here. So the first thing is that we have a Vmax, which occurs at the center of the pipe, and its magnitude is equal to 5 feet per second. Additionally, we have the pipe diameter. The pipe diameter is equal to 6 inches. And then we have the density of water. This one was given. It's equal to 1.94 slugs per cubic foot. Okay, and what we're looking for here is the mass flow rate. We're not sure what the mass flow rate is. If you recall, the formula for mass flow rate, m dot, is equal to density times area times speed. Now, this is true if you have a flat velocity profile. This is kind of assuming that you have an average profile where the V is all the same, right? This is all equal to V max, but that's not our case here. So what we could do instead is we could compute what the differential mass flow rate is, and that's equal to rho times V times dA. And what we would do is kind of integrate both sides of this. Now I know what you're thinking. You're seeing integrals here in the fluid mechanics section, and you're kind of writing this problem off as not realistic for the FE exam. But integration is just geometrically computing volumes. Don't be afraid if you see an integral. It's going to be super easy to compute, and you could actually do this one by inspection. Let's talk through the thought process about how you would go ahead and compute this integral. So when you integrate all of the little masses, all the little mass flows, you get a total m dot. You can take the rho out of this integral. What you get is the integral of v dA. We're taking that rho out because we're assuming this is a liquid and its density is not going to change. So it's constant. That means we can take constants out of the integral. We have the integral of VdA. This is called the volumetric flow rate Q. What does it physically represent to take the product of V and dA? I drew a little schematic down here with a typical dA we would use for a problem like this. It's an annulus, and we would take that annulus, that dA. This one is an individual one shown here, and we would raise it up all the way up to this velocity profile till it touches the surface. It would kind of touch here and here. What you get is a cylinder, but as you kind of add up all those little VDAs because of this integration sign, overall what you get is a cone. That cone would have a radius. The radius of that cone is equal to half the diameter. And what about the height of the cone? The height of the cone, h, would be equal to V max. So you can see we didn't really have to do any integration. All we did was found a volume. This is very similar to the video that we just did on, fluid statics, where we were finding the volume under that pressure distribution to compute a force. If you haven't seen that video, go and check it out. Conceptually, these problems are more difficult compared to, actually doing the arithmetic, right? We're really just computing a volume. This problem is more conceptually difficult compared to, plugging into more formulas. Okay, so now we know what that cone volume is. We can substitute in for that volumetric flow rate. Geometrically, it's just the volume of a cone. Physically, we're computing a volumetric flow rate. The volume of a cone is 1/3 pi times r, which was d over 2, squared, multiplied by the height of that cone, which was equal to V max. Okay, now all we have to do is plug into this formula right here, and we get the answer. The mass flow rate is equal to the density. The density was 1.94 slugs per cubic foot, multiplied by 1/3 pi. The diameter we have as 6 inches, divided by 2, that's going to be 3, squared, multiplied by V max. And we know that V max in the center was 5 feet per second. I usually work on my units on the right-hand side of the problem just to make sure I don't get them kind of jumbled up with the numbers. So let's go ahead and do that. We know that the density is measured in slugs per cubic foot. We have the pipe diameter. That one is measured in inches. And we know that we're going to square those inches because it's a d squared term. There's also a V max, which is measured in feet per second. We can go ahead and convert all of this into feet, right? Because we're looking to cancel out all of those feet. And we know there's 12 inches in a foot. Go ahead and square that side. We get rid of all those inches. Now, if you recall from those choices, if we quickly look back, all the choices are in pounds per second. If we're looking for the choices in pounds per second, that's going to mean we need to convert this slug into pounds. There is 32.2 pound mass in a slug. So let's go ahead and use that information. In one slug, there is 32.2 pound mass. So I always remember the 32.2, that's the gravitational constant in English units. But what you might forget is which one is heavier. And just kind of try to remember that a slug is really heavy. It's actually like 32.2 pound mass, right? So it's a good way to remember it, right? A slug is really heavy compared to a pound mass. Okay, so the slugs end up canceling out. All the feet cancel out. All the inches cancel out, and we end up with pounds per second, which is exactly what we want. Let's go ahead and plug this into the calculator. If you're enjoying the video thus far, please leave a like and subscribe. It lets me know that you're enjoying the content, and I'll make sure to keep putting out content like this. Let's get back to the video. This is equal to 20.4 pound mass per second. Let's go ahead and close this answer and check the solution. Let me know in the comments below if you got this question right or not. What did you think about that integration that we did? Okay, if we quickly kind of review what we did here, we saw that Vmax was 5 feet per second. And we also knew that the radius of the pipe that was given, we said that geometrically, what we could compute to get that integral of VdA, that was just the volume under the velocity distribution here. The volume under that distribution was a cone. That's just 1/3 pi r squared times the height. And we went in and did that integration by inspection, and we were able to compute a mass flow of 20.4 pounds per second. If you enjoyed the video, please leave a like and subscribe. Thanks for watching. I'll see you in the next video. Goodbye.